All right, so in chapter was it 8 and 9, we were looking at structures of different molecules. So we saw the Lewis structures and then the Vesper models, where we were considering the three-dimensionality of them. And then in chapter 10, we started to look at gases. So if we think about what we've covered, 8 and 9, we were thinking about forces that are holding together one molecule. And then in chapter 10, we were basically thinking about matter that's going to be independent of each other. So thinking about gases, there's not going to be really any attractive force between those different gas molecules. But now what we're going to look at is intermolecular forces. Gases do have some intermolecular forces, but for the most part, they're independent of each other. Now we're going to look at liquids and solids, excuse me, and see what's holding together those different substances. So with it, we're going to be, like I said, thinking about liquids and solids. But even the gases that we've already talked about will have a small amount of intermolecular forces. So if we think about the prefix inter, just like an interstate is going to be a road that goes between multiple states, these intermolecular forces are going to be what's holding together different molecules. So if we think about just a cup of water, what's holding together all of those different water molecules? Why aren't they just going completely separate from each other into the gas phase? And when we're looking at the different states of matter, the relative strength of the intermolecular forces is going to increase as we go from gas to liquid and then liquid to solid. So as we have those molecules get closer and closer together, the strength of that interaction is just going to increase. So as we cool down a sample, typically we see the intermolecular forces are going to get stronger. And we'll be able to use these intermolecular forces to understand why solids are going to have sort of that tight structure, that organization to the way those molecules are going to be set up. And then liquids get a little bit more free flowing. And then the gases we've already talked about, like I said, are going to be essentially independent of each other. And then with the solid and liquid, that's what we'll be focused on for the most part here. We'll see the transition into the gas state. So we'll look at boiling, for instance, or sublimation if we go from the solid straight to gas. But when we're looking at the solids and the liquids, since both of those are going to be similar in the sense that the molecules or the atoms, if it's just a pure element, are going to be close together. So we can refer to them just as the condensed phases, whereas the gases are going to be completely spread out. And then with it, just so we review some of the properties of these different states of matter, with the gases, as we've already talked about, they fill the entire volume and shape of the container in the container they're in, excuse me. And then they're also compressible. So that's why if we had a balloon, we walk all the way up to the top of a mountain, we're going to see the balloon expand. We can just as easily take that balloon and squeeze it. We can compress those molecules closer and closer together. That's why the volume and the shape aren't going to be constant. But then with the liquids and the solids, now that we've got those molecules closer and closer together, we'll see that the volume is going to be constant for both of them at a given temperature. And then with the shape, we'll see that's constant for the solids as well. And then neither of these is going to be really compressible. They will, to a very small degree, be compressible, but for the most part, regardless of the pressure, the volume of these types of substances are going to be the same. And then, like I mentioned before, the intermolecular forces, these are going to be what's holding together different molecules. We're going to see a couple different types of intermolecular forces. So depending on what type of substance it is, the interactions between those different molecules is going to be different. That's why we see some of the different properties that we're going to talk about. But with these intermolecular forces, they're going to be much weaker than the intramolecular. So an intrastate is a road within one state. Intramolecular forces or attractions are going to be the forces within one molecule. Those are going to be much stronger than what we're going to be talking about here. So the forces in between two molecules is going to be much less than the force within one. So if we think about the covalent bond in something like hydrochloric acid, that's going to be a much weaker or much stronger interaction, excuse me, than the interaction between separate hydrochloric acid molecules. But these, like I mentioned, will affect the properties of those substances. So we're going to talk about phase changes, so boiling and melting points, vapor pressure, and then we'll see viscosity as well. And then the overall group we can kind of put these interactions into is just the van der Waals forces. But we're going to see the specific types of them. So dipole-dipole, hydrogen bonding, and then London dispersion. Before we look at those, there's also going to be, and then there's even a different type of interaction than this one, but with ion dipole, if we just break down what that is, an ion is going to be something that's either positive or negatively charged. And then a dipole is just going to be something that's got a positive and a negative end. So what we're looking at here at the bottom could be something that's going to occur when we dissolve an ionic substance. So with those ionic substances, we'll have a cation and an anion. And then when we take it and dissolve it in water, it dissociates into those individual ions. And then the water molecules, so you can think about the red here as representing the oxygen, and then the blue or purple, whatever color that is, would be the positive hydrogens. So for the cation of that ionic substance, we wind up having the dipole interact with the negative end, because opposite charges are going to attract. And then just the reverse for the anion, we see it surrounded by the positive hydrogens. This is going to be what's actually occurring when we dissolve ionic substances, and this is going to be the reason that they dissolve. This force is going to lower the energy, or this interaction, I should say, is going to lower the energy, and it's going to be more favorable than having just the intact ionic substance. Remember, we're always trying to decrease energy. And then with it, we'll see something similar with ionic substances, just as the regular ionic substance. And we're not really going to talk about it here because we've already looked at it with just ionic compounds in general. But with ion dipole, we've got an ionic substance, so we've got the ion and then the dipole having both sort of pieces, and we can see how it arranges. But there's also what's known as ion-ion interactions, but those are going to be exactly the same thing as an ionic bond. So we're not really going to talk about them at all. But if we think about just removing all of these water molecules, if that's what we want to think of them as, we would then just have the positive and the negative, positive and negative ion from the ionic substance. There would then be some sort of attraction between those because we've got the opposite charges, so they'd be drawn together. And then if we think about a larger ionic sample, so if we just had more of that same thing, we would have that exact same type of interaction occurring between just different ions. So we'd have more negative ones surrounding the positive ion, more positive ions surrounding the negative. So when we're looking at an ionic substance, you can kind of think of the intermolecular force and the intramolecular force as exactly the same thing, because that type of interaction is occurring with multiple of those ions. But then with the next one, dipole-dipole, so if again, we just think about what that means, dipole is a molecule that's got a positive and a negative end. So a dipole-dipole interaction is just going to be the interaction between two of those molecules or multiple of those molecules. And if we think about what could occur, we could have negative and negative, going to be repulsion, positive and positive, going to be repulsion. But the attractive force here is going to be when we have a negative end of one molecule and a positive end of the other, interacting like we see with all of these different red lines here. And then with these interactions, just like if you think about ever having two magnets, if you have them super far apart, there's really nothing interacting between those two. We're going to see the same thing with these dipole-dipole interactions. We need those molecules relatively close together in order for this interaction to be meaningful. So that's why when we look at gases, for instance, we can say that they have essentially no intermolecular forces, just because those molecules are going to be far apart. They're going to be moving pretty quickly. So this sort of attraction is going to be minimized. And then with the dipole-dipole interactions, we're going to see that as the size of that dipole increases, the strength of the intermolecular force is going to increase as well. So if you look, we've just got a handful of substances here, and then they're all relatively the same in the sense that we've got a methyl group, so CH3. Then we've got different things coming off of it. So we've got propane, which is just a couple more carbons with hydrogens filled in. Then we've got dimethyl ether, which is essentially just two methyl groups on each side of an oxygen. Methyl chloride, just added a chlorine, acetaldehyde, and then acetonitrile. And then we can see with the table here, the dipole moment, essentially just showing us how polar is that molecule. The larger the dipole moment, just the larger the positive and negative pieces of that molecule are going to be, basically. And we can see as that dipole moment increases, and we should also look at the molecular weight. They're all relatively close in size. So that's why we can compare these ones just based on the dipole moment. We'll see with some of the later forces, the size of these molecules is gonna be important. But since they're all relatively similar in size, we can focus on the dipole moment. And we see just as we go down this table, these molecules are becoming more and more polar. And that's why if we also look at the next column, we can see the boiling point is increasing as well. And the reason for that is, if we go back here, as this dipole becomes larger, so as this positive end becomes stronger, negative end becomes stronger. So you think that's going to have to balance out the neutral anyway. So we could have like negative a quarter of a charge, positive of a quarter of a charge, or however you want to think about it. But then we can make those charges larger. And now the interaction between the positive of one molecule, the negative of the other, is going to become stronger. So we'll have those molecules more tightly held together. It's going to take more energy then to separate them. And that's why we see the boiling point increase because of that. So with these intermolecular forces, we're not changing anything about the molecules themselves. We're just looking at the interactions between different molecules. And that's why we're going to be focused on phase changes. Because with these phase changes, we're essentially just changing the level of interaction between those molecules. And then as the interaction itself is stronger and stronger as we go down the table, it just takes more energy in order to separate those molecules. And we see a similar trend with the melting point too. So we could look at the other phase change. And then with these intermolecular forces, if we think about what we just talked about, dipole, we need a polar molecule. We need the positive and the negative end of that molecule to be present in order for those ends to interact with other molecules. But now when we look at London dispersion forces, this is going to be something that we'll see in every substance. And the reason we'll see it in every substance is if we just look at something simple like a helium atom. So it's going to have a positive 2 charge on the nucleus because it's atomic numbers 2, which means we'll have 2 electrons as well. And if we think about these electrons as just kind of flying around the nucleus, they're in the electron cloud just doing their thing. There's going to be a negative charge on each of these. So in general, they're going to want to stay far apart. That opposite charge, or the like charge, is going to repel. But if we think about them as just kind of flying around, every once in a while, we'll wind up with these electrons on the same side of that atom. And when that occurs, we're going to have what's known as a temporary dipole, because we think it's really just a neutral atom. But every once in a while, if we've got both of the electrons on the left-hand side, for instance, now that side of the atom is going to be temporarily negatively charged, and then the opposite side with the nucleus is going to be temporarily positively charged. So what we're going to see is if we then take that atom and place it next to another helium atom, the temporary dipole from one atom is going to induce a dipole in the other one. So if you look at helium atom 2 here, we've already got both electrons on the left-hand side. So now we've got a negative charge here. So now if we put another helium atom next to it, this negative charge is going to affect that atom. It's going to essentially push the negative charge of that other atom further to the left then. And now we wind up with a second temporary dipole. And this is going to be the interaction that's going to be present in every substance, but it's going to be the only interaction that's present in nonpolar substances. But it's also going to be a very, very weak interaction. We'll still have the positive and the negative ends, but they'll only last for a very, very brief instance, and they're not going to be very strong to begin with. And that's why we can refer to it as an instantaneous dipole. In the one case, because it's only lasting for a very brief moment, and then an induced dipole in the other one because it's occurring as a result of that first one. And then like I mentioned, This force will be present in every substance, but it's going to be the only force that's present in nonpolar substances. And that's why we'll ultimately see, since this force is weak, nonpolar substances are going to have relatively low boiling and melting points. But then the property here of having the electron cloud get distorted, so having both of the electrons located on one side, so we have this temporary dipole or instantaneous dipole, that's going to be referred to as polarizability. And we're going to see that this property is going to increase with the size of these molecules. So as we have essentially more electrons, more room for those electrons, it's more likely to have something like this occur. And that's why we'll see this London dispersion force is going to increase with size. And then in addition to size, which I think we'll see in a few of these. Yeah, the next slide, actually. What we'll see if we look at organic molecules is that the shape of these molecules is going to be important as well. So if we look at N-pentane and neopentane, what we're going to see with N-pentane, where we've just got a linear molecule, so just all of those carbons are going to go in a straight line, whereas neopentane, we've kind of got branches, so it's almost like a ball. What we're going to see is the more linear molecules are going to typically have higher boiling points, higher melting points, just stronger intermolecular forces, because with these molecules, they'll essentially be able to stack and sort of interlace with each other almost. And that's going to make it harder, make it more difficult for those molecules to then be separated. Whereas the neopentane, where we've got this branch structure, again, kind of just looks like, if we look at sort of the overall structure, kind of just looks like a circle. Now they're not going to fit together as well. It's going to be more easy to separate them. So that's why we see N-pentane has a boiling point of a little over 300, whereas neopentane is about 30 degrees lower. And then with this, as I mentioned before, we're going to typically see that polarizability is going to increase with size. So if we look at the halogens or we look at the noble gases, we'll see a similar trend in the boiling points as we go down, and we see the same thing with the melting points as well. But as we go down these groups, we're going to see the boiling point increase because of the larger molecules. And then with these, the reason we can focus on these two groups is because with these two groups, the only interaction we're going to have is that dispersion force, just because these are going to be nonpolar substances. So with the noble gas, it's just that atom, and then we're surrounding it with other atoms, basically. So there's going to be no positive or negative piece other than just like we saw with helium, when we had temporarily sort of a uneven distribution of the electrons within one of those atoms. We'll have a temporary dipole, which will then induce a dipole in the other atoms. But it's going to be a very weak interaction. It's going to be a nonpolar one, just like with the halogens. Now we've got those diatomic molecules. But since each of those atoms is going to have the same electronegativity, so two fluorines are going to be equal to each other. Same thing with two chlorines or two bromines, two iodines. So we're not going to wind up with a positive or negative end there, except for in the case where we just have an uneven distribution of the electrons for an instant. So when we look at either of these groups, we can see the molecules are increasing in size. So the molecular weight is shown here. But if we also just think about the number of electrons, we'll have more of them present in iodine than we will in bromine, than we will in chlorine or fluorine. And the same thing as we go down group 18. So that's why when we look at the boiling points, we can see those increase as well. So helium boils at less than 5 Kelvin, whereas xenon, 166, so still a very low temperature, but much, much higher than the helium. We can see it increase throughout that group. And then the same thing with the halogens. Fluorine and chlorine are both going to be gases at room temperature, just because that intermolecular force, that London dispersion, is going to be weak. But then with bromine, we see a larger molecule. We've got a stronger dispersion force there. And that's why bromine is actually going to be a liquid at room temperature. And then iodine, we increase that interaction even more, just because it's an even larger molecule now. So that's why iodine is actually a solid at room So we can look at the intermolecular forces to see the different states of matter for these different elements. And then with this one, which have a greater effect, dipole-dipole interactions or dispersion forces? If we're looking at two molecules that are roughly the same size, so if we think again back to that table where we had 5 different substances, or 5 or 6 with the dipole moment shown, we saw the dipole increase as we moved down that table, so the boiling point did as well. And the reason we could look at the dipole-dipole interaction in that case is because the size of those molecules was approximately the same. Of course, not exactly equal, but they were roughly the same size. So that dispersion force is going to be about equal within all of those. So the dipole-dipole interaction is what played a larger effect in the boiling point or the melting point, whatever one we looked at in that table. Whereas if we've got 2 different molecules and one of them is much, much larger, now it's going to have a much greater dispersion force. So even if the dipole-dipole interaction is much lower, the dispersion force may be much greater. So in that case, we've got to consider both of them. And if we look at a couple of trends, we'll see as we go from methane to silicon tetrahydride, germanium tetrahydride, tin hydride, we've got an increase in the boiling point with an increase in the molecular weight. So we're essentially taking 4 hydrogens and then just moving down group 14 in terms of that central atom. So that central atom is increasing in size. We see the temperature increase as well with the boiling point. We see something similar if we look at 2 hydrogens and then we're going down group 16 with that central atom. So tellurium, selenium, sulfur. As we go up that group, that molecule becomes smaller. So we see the temperature, the boiling point or melting point, we're going to see that decrease. Whereas with water, even though it's a much smaller molecule, we now see a extremely high boiling point, 100 degrees Celsius at standard pressure. And the reason for it can't be explained with the dipole-dipole interaction or the dispersion force, because if it could, we would expect a similar trend as we see in blue here. But what we're going to see with water, and we see it in other substances as well, so like ammonia, and one of the reasons life on Earth is even possible is just going to be because water can participate in what's known as hydrogen bonding. And with it, it's essentially a dipole-dipole interaction. So we're going to have a positive or a polar molecule. We'll have a positive piece of that molecule, so the hydrogen in water's case, interacting with the negative oxygen of the other. And with ammonia, we see the same thing. It's just with nitrogen rather than oxygen there. But with this interaction, we're going to see it's unusually strong. And with it, we'll have something similar with fluorine as well. So one way to kind of remember it, it's a pretty stupid saying, but hydrogen bonding is fun, F-O-N, fluorine, oxygen, or nitrogen. Because we're going to, in order for this to occur, we're going to need hydrogen bonded directly to one of these atoms. So in some cases, we'll see examples where we'll have a fluorine or an oxygen or a nitrogen with hydrogen in a compound. But if they're not bonded directly to one another, we're not going to have the electronegativity difference we need in order for hydrogen bonding to occur. But like I said, we're going to have essentially a dipole-dipole interaction. It's just going to be because oxygen or fluorine or nitrogen are going to be extremely electronegative. We're going to wind up with essentially the largest dipole-dipole interaction we can. So if you look at it, in this case, we're again looking at water here. What we're going to see is that those water molecules are going to kind of arrange themselves so that the negative end of one is pointed at the positive end of another. And then because we're going to have these polar molecules, we're going to have hydrogen with an extremely electronegative element, something like oxygen or fluorine or nitrogen. We're going to wind up with large positive and large negative charges for these polar pieces. So it's going to increase the strength of that interaction. Essentially, we're just increasing the dipole moment. But then what's also occurring is if we think about what happens to hydrogen, it's only got that one electron to begin with. It's going to share another, it's going to get a shared electron from that other atom to form the bond. But now if you think about this atom, we got the two electrons and they're going to be shared between those two atoms. So now that hydrogen atom is kind of, or the nucleus in particular, you can kind of think of it as now it's exposed because we've got the negative piece on the other end. We've only got the nucleus here. So we're going to have a strong interaction with the negative oxygen from another molecule, or same thing if we had a nitrogen for like ammonia or a fluorine in hydrogen fluoride even. But that's going to increase the strength of that interaction in that way. And that's why we're going to see hydrogen bonding is going to be much stronger than the dipole-dipole interaction, or the regular dipole-dipole interaction, I should say. And that's why if we go back to the table quick, that's why we see water has a much higher boiling point than any of these other substances here, because hydrogen, or water, excuse me, is going to be able to participate in hydrogen bonding, where none of these other molecules are going to be able to. So that's going to be a much stronger intermolecular force. It's going to take much more energy in order to separate water molecules. And that's why we see it boil at such a high temperature. But with these, if we look at them all quick, each of these also has hydrogen. But because they don't have hydrogen with fluorine, oxygen, or nitrogen, that's why we can't have hydrogen bonding occurring. But one of the reasons, like I said, life on Earth is possible is because of this hydrogen bonding. That extremely high boiling point allows liquid water to be present on Earth. And if it wasn't, we just wouldn't be able to survive, of course. And then there are other factors as well. So the way water freezes, ice forms on top, allows the organisms in things like lakes and that to survive in the winter. They're not exposed to the extremely harsh conditions. So there's a whole bunch of interesting things that go on with water. But now if we look at this table here, we've got kind of a little flow chart we can use to identify the strongest intermolecular force that's going to be present in a given substance. And as we're going through this, we want to first just think about, are ions going to be involved? If the answer is yes, we want to think about, is it ions with a polar molecule, or is it just ions by themselves? So if it's ions just by themselves, we're going to have just the same thing as ionic bonding. So that's why I said the ion-ion interaction is the same thing as the ionic bonds. Just the positive and negative pieces are attracted to one another. And it's just kind of dependent on if we're looking at one single molecule. So if we're thinking about one molecule of NaCl, we could think of that as an ionic bond. And then if we had a whole bunch of sodium chloride molecules, then we could think of it as the intramolecular force. But if we've got polar molecules there, now we'll have the ion dipole force. So this is like when we take those ionic substances and dissolve them in water. Now we'll have the potassium bromide dissociate, and we'll have the positive cation surrounded by the negative oxygens. And then the negative bromine is going to have the water molecules surrounding it, so that the positive hydrogens are going to be sort of pointed at it. But if no ions are involved, now we're looking at the van der Waals forces. Dispersion forces are going to be present in everything, but those will only be present, or those are the only force present, I should say, in nonpolar molecules. So if we've got a noble gas, for instance, or a diatomic halogen, something like iodine, all we're going to have is that dispersion force, because we're only going to have those temporary dipoles by the uneven distribution of electrons. But if we do have a polar molecule, then we need to identify if hydrogen bonding is going to occur. So if we've got hydrogen bonded directly to fluorine, oxygen, or nitrogen, remember, hydrogen bonding is fun, then we can have that stronger dipole-dipole interaction. We can have that hydrogen bonding occur. But if we don't have one of those electronegative elements bonded directly to hydrogen, that's when we're looking at the dipole-dipole forces. So if we look at a couple problems here, and I'll give you, if you want to kind of work through any of these on your own, and I'd recommend you do that so you can kind of give yourself a chance to think through everything. Just pause it for a moment as I go to each of these new slides, but I'm going to kind of just go through them so we don't have just a minute or two of dead time on each of them. But for the first one, the dipole moment of acetonitrile, so we've got a methyl group with a cyanide coming off of it, and methyl iodide are 3.9 and 1.6. So D is just kind of the unit for that dipole moment. So 3.9 for acetonitrile, 1.62 for methyl iodide. We want to answer these three questions using that information. So which of these substances will have the greater dipole-dipole interaction among its molecules? So since acetonitrile has the larger dipole moment, we'll see a greater dipole-dipole attraction within that substance. So if we had a sample of acetonitrile and a sample of methyl iodide, the acetonitrile is going to have the stronger dipole-dipole interaction. But since the iodine is going to be so much larger than a carbon and nitrogen, so they each got the CH3, so we want to focus on that other piece. Since the iodide is going to be so much larger, we'll have more of the London dispersion force with that one. And that's why if we look at the boiling point, they're reasonably close, so 355 to 316 basically. But since the acetonitrile has the higher boiling point, that means it's going to need more energy in order to separate those molecules. So it's going to have the greater overall attraction there. So in this case, the dipole-dipole interaction is going to be more important than the London dispersion force will be. If it was the other way around, if methyl iodide was a little bit bigger, then that dispersion force would increase even more. And then we may have this boiling point be higher than acetonitrile. But in this case, the dipole-dipole moment is going to be the strongest interaction there. And then for the second one, now we've got a handful of different substances. We want to do kind of the same thing. Which of these is going to have the strongest dispersion force? Which of these is going to have the strongest dipole-dipole attraction? So with the dispersion force, again, we want to just think about which of these is going to be the greatest in terms of size. And with it, neon, nitrogen, hydrogen, chlorine are all going to be pretty small atoms. Bromine is going to be the largest. So we're looking at either diatomic bromine or hydrobromic acid. But since the second bromine is going to be so much larger than the hydrogen here, the answer to A would just be that diatomic bromine, just because that's going to be by far the largest substance we have. So if we think about neon, it's just one atom, it's fairly small. Nitrogen, two of them that are both pretty small. And then with chlorine and bromine, bromine's going to be greater. And then a second bromine will be larger than that first hydrogen there. And then with the second one, the largest dipole attractive force, now we want to think about which of these is going to be the most polar molecule. And with it, we can eliminate bromine, neon, and nitrogen. So all of those are going to be nonpolar. Neon's just one atom by itself. Bromine and nitrogen are the same atom, so there's going to be no electronegativity difference there. We want to look at HCl and HBr. And in this case, we're going to wind up with HCl being the largest dipole attractive force, because chlorine is going to be more electronegative than bromine. So we'll wind up with a larger dipole moment here. So we'll wind up with a larger dipole attractive force because of it. And then with the next one, we want to identify which of these could participate in hydrogen bonding. So remember, hydrogen bonding is fun. So even though we've got hydrogen in all four of these substances, doesn't necessarily mean we'll have hydrogen bonding. Methane and hydrogen sulfide, we can eliminate those two immediately because we don't have nitrogen, oxygen, or fluorine there. So we need one of those elements bonded to hydrogen. So because we're missing those elements completely, we can eliminate the first and the last one here. And then with the middle two, hydrazine, we've only got nitrogens and hydrogens. So there has to be a nitrogen bonded directly to hydrogen. So we could have, and we will have, hydrogen bonding occur in hydrazine. We'll actually have it quite a bit because we'll have each of these nitrogens bonded to two hydrogens. And then with the methyl fluoride, in this case, we will have hydrogen, we will have fluorine. I didn't bring my mouse with me, so I'm doing this just on the laptop pad thing, so it's coming out a little terrible. But with methyl fluoride, we're going to see we'll have that methyl group with just a fluorine substituted for one of those hydrogens. So even though we've got the elements we need, we're not going to have the fluorine bonded directly to that hydrogen. So we don't have those atoms bonded together like we need them. So we wouldn't actually have hydrogen bonding here. So we'll only have it in the hydrazine, excuse me. We won't have it in any of the other molecules listed there. And then I think we got two more, maybe. Three, four. Oh, okay. I thought, okay. So we got a couple more examples we'll look at here before we wrap up this video. But list the following substances in order of the increasing boiling point. So we want to think about what types of interactions we're going to have in these ones. And with it, I'm going to put the number above it. So 1 will be low. 5. So with it, we want to think about what type of force we'll have in each of these. And in hydrogen, diatomic hydrogen, as well as neon, we're only going to have dispersion forces because both of those are going to be nonpolar. And then with the hydrogen, since it's smaller, even though we've got 2 atoms, each of those is going to be much smaller than a neon atom. So we'll have less of that dispersion force in hydrogen than we will in neon. So we'll see hydrogen's going to have the lowest boiling point. Neon's going to have the highest, or of those two, it'll be higher. And then, ooh, that was a terrible 5. And then sort of skipping ahead, if we look at the first substance there, barium chloride, that's going to be an ionic substance. So we'll have ion-ion interactions. And those are going to be still a bad 5. But those are going to be the strongest interactions we have. So that'll boil at the highest temperature, and that's going to be the highest by far. So with the final two, in this case, we've got 2 atoms in each, and they're both different atoms. So we're going to have an uneven sharing of these electrons, so we'll have a polar molecule. But with carbon monoxide, the strongest interaction we'll have is that dipole-dipole interaction. Whereas hydrogen fluoride, we've got hydrogen and fluorine bonded directly to each other. We can have the hydrogen bonding occur then. That was bad too. So since we can have hydrogen bonding occur with the HF, we're going to have a stronger interaction. It's going to take more energy to separate those. We'll see a higher boiling point because of it. So when we're ranking them, hydrogen would be the lowest, followed by neon, carbon monoxide, hydrogen fluoride, and then finally barium chloride would boil at the highest temperature by far. And then what intermolecular forces must be overcome to, and then we've got a couple different processes. So boil water, so going from liquid to gas, sublime solid iodine, so we're going from solid to gas, and then melt magnesium chloride. So with all of these, we're going to have dispersion forces, just because those are going to be present in everything. And that'll be the only force we have in B. So remember, that's a nonpolar molecule. That's all we're going to have there. So in order to sublime iodine, we would only need to overcome that weak dispersion force. Would be relatively strong for iodine just because it is a fairly large molecule in terms of diatomics. But it's going to be much weaker than the ion-ion interaction we would have with magnesium chloride. And then with the boiling water, again, like I said, we'll still have dispersion force with all of these, but with boiling water, we'll have H2O. So we'll have hydrogen and oxygen. We'll have that hydrogen bonding. Again, that's why water boils at a relatively high temperature for a molecule of its size. And then the strongest intermolecular force in methyl bromide, diatomic bromide, calcium bromide, and ammonia. So with the ammonia at the bottom, nitrogen and then hydrogen, and they're going to be bonded directly to each other. We'll have hydrogen bonding. With, if we just go through these the rest in order, with the methyl bromide, we've got hydrogen, but we don't have it with any of the necessary elements. So this is just going to be a central carbon surrounded by 3 hydrogens and a bromine. But since we've got different terminal atoms here, so we've got 1 bromine versus 3 hydrogens on the outside of this carbon, we're going to have a dipole moment. So we'll have a dipole-dipole interaction if we had a sample of methyl bromine. Whereas if we just had diatomic bromine, it's going to be a completely non-polar substance. So the only interaction we're going to have is that weak dispersion force. And then with calcium bromide, now we're going to have that ionic substance. So we'll have the ion-ion interaction there. And then the last one. So which of these is going to have a higher boiling point? So we want to think about what type of force we're going to have in each case. And for the first one, oxygen versus nitrogen, diatomic in each case. These are both, of course, going to be nonpolar. So we're only going to have that dispersion force. But that dispersion force is going to be a little bit larger in oxygen, just because it's a little bit larger atom. So we'll have a little bit more of that dispersion force occurring. And then with B, we've got two substances that look very similar, sulfur dioxide, carbon dioxide. But with it, what we'll see is sulfur dioxide is going to be a much higher boiling point for a couple reasons. If we didn't get the Lewis structure correct, we may think both of these atoms, or both of these molecules, excuse me, are linear. Won't be the case though. Carbon dioxide is going to be linear. Carbon dioxide is going to be nonpolar because of it. So carbon dioxide will only have that dispersion force. Whereas sulfur dioxide, we're actually going to have a lone pair on that sulfur. So we'll wind up with a bent molecule. So it'll be polar. We'll have a dipole-dipole interaction. So it's a stronger interaction. But also, if we just look at these two, sulfur is going to be, and you'd want to make sure you pay attention to the polarity, because if carbon dioxide was polar and sulfur dioxide wasn't, we'd see the reverse. But in this case, if we didn't identify that, we could also just see that since sulfur is larger than carbon, we'd expect a larger dispersion force there. But since these are roughly the same size, we would want to pay attention to the dipole-dipole interaction. And that's why sulfur is going to be much greater. And then with the third one, HI versus HF, if we only focused on the dispersion force, we'd expect hydrogen iodide. But since we've got hydrogen bonding there, we'd expect the hydrogen fluoride to have a higher boiling point. And then with the next one, these are going to both be nonpolar just because they'll have the tetrahedral structure. But with germanium hydride, we're going to have a larger central atom there with germanium versus silicon. So we'll see the higher boiling point because of it. And then with E, lithium is going to be larger than hydrogen. But also in the case of lithium chloride, now we've got an ionic substance. So we've got the ion-ion interaction going to be much greater than the dipole-dipole interaction we see with HCl. So that's why lithium chloride is going to have a much higher boiling point. And then with the final one, these are both just going to be organic molecules. So ethane versus butane. And with butane, we've got a couple extra carbons, a couple extra hydrogens. So we're going to see a larger boiling point there just because of the increased dispersion force. So we've already kind of alluded to it with the different the boiling point and melting point and things like that. But what we'll see in the next half of this chapter is just some of the other properties that can be affected by these intermolecular forces.